So here's section 4.2. And before we do the warm-ups, I think you can actually do a few basic examples of this yourself which will help understand it. But I'll give you the definition first here, which is that we say that a function f has a global maximum at x equals p if f of p is greater or equal to f of x for all values of x. And it's basically the same definition for a global minimum if at x equals p, if f of p is less than or equal to f of x there. So this is just my notation to include both of them the same thing. This is the definition of a local max, and this is the definition of a local min. Either way, it has to be greater or less than, whichever way it is, than all other function values of x. So I'll show you what that looks like here in this graph. I'll do warm-up 1 for you and then let you guys try the rest of these on your own. So with warm-up number 1 here, well, let's first look for local mins and local maxes. So I see a local maximum at x equals 3 right here, because f of 3, which is over here, is greater than the other values of f near it. If you plug in something like 2.9 or 3.1, you get something a little less than that on the y-axis. So 3 is 1, and then also here at 6 there's another one, because f of 6 is a little bit bigger than f of 5.9 or f of 6.1. So that's a local maximum there. Then there's a local minimum at x equals 5. Because at x equals 5 here, the f of 5 is a little bit less than f of 4.9 or f of 5.1. This point is a little bit lower on the graph than all the other points around it. So that's a local minimum. Now let's look at a global max. And so a global maximum here would be a point where the highest point on the graph everywhere. So that point is right here. So it's not just higher than the other points around it, it's higher than all of the other points. So f of 3 is greater than f of 6 and all of everything else. So the global maximum is 3. And then the global minimum, let's think about this. It's not 5 because you can see that f of like 1.1 here, 1.1 is a little bit less than that. And you could actually plug in something even closer to 1, like 1.01, and I can't really draw on the sloppy graph, but you can get closer and closer to this point without ever reaching f of 1, and all of those points, as you get closer, the y coordinates are just getting a little bit less and a little bit less. So there is no global minimum here. So that's the difference between a local minimum and a global minimum, and you can also see why sometimes a minimum or a maximum doesn't exist when you can just get closer and closer to this point where it's undefined. So just to explain that a little bit more, you might want to skip this if you understood it and if this one seemed easy, and go on to the rest of these warm-ups. But just to explain that a little bit more, if I were to do f of 1.1, that would be like this coordinate here, and that's a little bit greater than these other y coordinates, like f of 1.01. And that's just a little bit greater than f of 1.00001. And you could keep doing this forever, and there's no minimum, because f of 1 itself, because of the empty hole, is undefined. So that's a little bit more explanation for why it doesn't have a global minimum, if just in case you weren't understanding that. So here's the rest of these warm-ups. These will help you understand what kinds of functions have minimums and what kinds of functions have maximums. We're going to explore this theory a little bit more in the section. So give these a shot. The answers will appear in 3, 2, 1. And here they are. So with warm-up number 2, there's a local maximum at x equals -4. That y coordinate there is higher than other y coordinates around it. And also at x equals 3, where it has that little peak there. That's a point where the derivative is 0, actually. Whereas -4 is an endpoint. And yeah, you might want to pay attention to these to see what kind of maximum or minimum is it, in the sense that, does it happen at an endpoint? Is it happening at a point where the tangent line is horizontal? Or is it happening at a point where the derivative is undefined, like at number 2 here? So yeah, and anyways, the global maximum is at x equals -4 because that is the highest y coordinate than anything. The local minimum is at x equals 2, but that's not a global minimum because there's other function values, other y coordinates over here that are less than it. And there's no global minimum for a similar reason as over here. It's just that if you plug in function values close to 4, there's no smallest one. You can just get smaller and smaller, this time getting closer to -infinity. So there's no minimum there, no global minimum, but there's a local minimum at 2. Anyways, this one has no maximums or minimums of any kind, or should I say no maxima or minima of any kind. And yeah, so you can see there's no point where the tangent line is horizontal. There's no point where there's a sharp corner like there was over here. And the endpoints aren't on the graph. So like 3 is not a maximum because, well, f of 3 is undefined with an open circle. And there's the same thing as before, where you do f of 2.9 is a little bit less than f of 2.99, and you can keep doing that, but there's no actual greatest y coordinate there. And let's see, so warm-up number 4 here, this has no maximum, yeah, because it keeps on going up forever there. And this has a local minimum at -6 and at 6. And actually, these are both global minima because notice that this says, because if f of -6 is equal to 6, then they can actually both be the minimum, because f of -6 works for p, because f of -6 is less than or equal to f of 6. So that means -6 is a global minimum, and vice versa. If p is 6, f of 6 is less than or equal, because it's equal, to f of -6. So that makes them both global minimum. So they're both tied there at the bottom. So I'd like to talk a little bit about why this is an important application of calculus in the world. So imagine that you're at any kind of place where there's people who have a function that models some kind of thing. Maybe it's a thing relating to money or some kind of engineering application, and you want to make something the best. That's what this is about. Is if your function represents how much money you make, or maybe it represents how cheap it is for you to make something, or maybe it represents the efficiency of a car. You want to make that result come out the best, and maybe you can adjust what the y coordinate would be. So for example, if you're making engines for cars, you might want to know, you might want to know what engine size, this is a super simplified example in liters, leads to the best miles per gallon with some constraints about how powerful the engine has to be. Like you want to make that engine the most efficient it can be. That's a weird example. Or maybe you're a bank and you are charging people interest rate on their mortgages, and you want to make the most profit or something. Maybe if you charge too little of an interest rate, you don't make any profit. And if you charge too much of an interest rate, nobody will take out your loans. So there's got to be some kind of point in the middle where there's the best interest rate that makes the most profit. And that's kind of what this is about. Or maybe you want to make something the cheapest, like if this is cost versus something else. So there's a lot of examples like that. I'll let you use your imagination. But as you can see, not every function is just like a nice thing like these ones where the only maximum or minimum happens when it's flat. There's all kinds of other ways you can get a maximum or a minimum. And there's different ways in which a maximum or a minimum doesn't exist. So you can see here, the ones that do not have a minimum on some of these are ones like, let's see, this one doesn't have a minimum or a maximum, and it doesn't have any critical points either. And notice that the domain of this, where the function values are defined, what x values make it defined, looks like this. It's the interval from -3 to 3, which doesn't include 3. If f of -3 were defined, and if it was this, and if f of 3 was defined, and it was continuous there, then those would be the minimum and maximums. Here, the domain of this one includes -4 and does not include +4. And so it ends up having a maximum there and no minimum here. This one, the domain on the x-axis where this is defined, is just that. So that way it ends up avoiding having a minimum, but it still has a maximum there. This one has a domain that does not include where this asymptote is here, but it does include -6 and 6. And at the places where it has an endpoint, it ends up having a minimum there. But the place where it doesn't include, where the domain doesn't include that, it makes it not have a maximum. So there's some theorems about this. One is, this is actually an important theorem in calculus, and hopefully it kind of makes sense. This is saying that if f of x is continuous on a closed interval from a to b, then f of x has a global maximum and a global minimum on that interval. And so the reason why you can imagine that this might be true is, let's say that you have your domain, which includes a and b, whatever these numbers are here, and all the numbers in between. Then whatever this graph looks like, it might go way up and then come down again or something like that. Who knows? It's going to have a maximum or minimum somewhere, and if it doesn't have a critical point, then it ends up having the maximum or minimum ends up being either at a critical point or at the endpoints like this. So this theorem, it's a little bit of common sense maybe, but it's actually a little tricky to prove, and we're not really proving too much stuff in this class. But it's mostly used to prove other things. Yeah, you can see that all of these functions here fail this in some way. None of these have a domain that is just a solid interval. The one that has an open interval as its domain here, this first one doesn't have a minimum because of that open interval. Same thing with the 4, same thing with -3 and 3, and same thing with this 0 in between. So this gives you a way of finding a general method you can use for approaching these kinds of problems, which we're going to have in this section in 4.3 and 4.4, which is that every local maximum that we learned about, this was from the last section, 4.1, every local maximum or local minimum is either a critical point, which is where the derivative is 0, or where it's undefined, like you have a sharp corner there, or where you have just a discontinuous function, maybe. That could be a minimum here. That makes f prime undefined at that point. So
Or it's an endpoint of the domain, which just means like this might have a maximum here and a minimum at the endpoint of the domain. So this gives you a way of finding them, which is if your domain is a closed interval, then this theorem applies, and it's going to certainly have a minimum and a maximum. And that minimum and that maximum must either be a critical point or an endpoint of the domain. So all of these things are what we call candidates. So you first find all these critical points, plug them in, and find the endpoints of the domain and plug them in, and we know that one of all of those candidates must be the maximum, and one of all of those candidates must give you the minimum. We just need to find out which one of them is the greatest, gives you the greatest output, and which one gives you the least output. And if your domain is something else, which isn't just that, like it's either all real numbers, which this theorem doesn't apply to, like for example, f of x equals x squared, if you just let it have its natural domain of all real numbers, this has no maximum. So this theorem doesn't apply. It doesn't necessarily have a minimum or a maximum. It has a min, the 0. X equals 0 makes f of 0 the smallest thing. So the theorem doesn't apply, so you kind of have to know what the graph is shaped like. X squared is shaped like this, and if you know that it goes off like that, approaching infinity in those directions, then you should conclude that it has no maximum. So you kind of need to know what the graph looks like, because you need to see whether its maximums and minimums even exist. And then you can find the critical points and their values partially to help you graph it, and also to see which one is the greatest and least, and to actually find them. So let's do an example here. Let's find the global max and the global minimum of this one on this interval. So first we're going to have to find out what the candidates are. So the things that are going to either be the minimum or could either be the minimum or the maximum are all going to either be the endpoints of this interval or the critical points of this. And I know it's definitely going to have them because of its domain is the closed interval that includes its endpoints. So first we need to find those critical points because we already have these two endpoints. So to get critical points, we need to set the derivative to be 0. Don't plug in 0. But just find g prime of x. That's going to be, let's see, 1 minus the derivative of sine is cosine. And here we need to use the chain rule because that 2x is like an inner function. And then we need to multiply that by the derivative of 2x, which is 2. So that's that. And this is going to be equal to 0 at critical points, or it could be undefined. But this derivative is never undefined because the domain of cosine is all real numbers. So we just need to have it set to 0. So to solve this, I'm going to add the 2 cosine 2x to both sides. Divide both sides by 2. And now we need to think about trigonometry a little bit. To think about what values of x within this interval make cosine of 2x equal to 1/2. So first of all, I like to think of a unit circle for this kind of thing. Okay, it's a little ugly, but we want to make the x-coordinate here become 1/2, so we can see what is the angle that makes the x-coordinate be 1/2 here. And I like to remember that I like to think of whatever you plug into 2x as an angle. So I'm going to say theta is 2x. So we're mapping, we're trying to find what is theta that makes this become 1/2 here. makes the x-coordinate 1/2. So this would be one angle theta, this would be another one down here. So that means, and yeah, you remember that it takes a 60-degree angle to get cosine to be 1/2, and it also has another negative angle down here, but we're actually not allowed to plug in a negative angle into this because x has to be positive. So if x is like negative pi over 3 here, then that won't work. So let's just write that we have theta equals pi over 3, or negative pi over 3, but we can't write it as negative pi over 3 because that makes x negative. So what's another way we could get this? What if we go around this way? That would be an angle of theta equals 2 pi minus pi over 3, also known as 5 pi over 3. It's been a little while since I've done very much trigonometry, so that's that. So then if we have that, that's really what 2x represents here. So we have that 2x is pi over 3, or 2x is 5 pi over 3. If you multiply each side of these two equations by 1/2, we'll get x is pi over 6, or x is 5 pi over 6. And let's see, 5 pi over 6 is actually not allowed because it has to be between 0 and pi over 2. So that one's out. This is the only critical point. So when you have that, we can then see what our candidates are. We've got 0, which is one endpoint, pi over 6, which is the critical point, and pi over 2 is the upper endpoint. So we need to find out what is g with each of those. So I'll save the tedium for you here and pause it. So these are the function values we've got, and we know one of these must be the the global maximum, and one must be the global minimum. So the least one we have is negative 0.34, and the greatest one we have is 1.57. So we can just make that conclusion here. Oops. So that maximum was at x equals pi over 2, and the global minimum is at x equals pi over 6. And just to see why it really works like this, let's just make a little graph of what this will look like here. So let's say that this is pi over 2, then pi over 6 is about a third of that. It's somewhere over here. And let's say this is 1, and this is about 1.57, and that will make this be negative 1 here. If we're going to make a graph of this, its domain is all of these numbers between 0 and pi over 2, and that's not the function itself. The function itself is going to look like this. It's going to have that point there, 0, 0, pi over 6, negative 0.34, which doesn't quite fit here, and then pi over 2, 1.57, which is about here. So everywhere else other than these 3 points, the derivative exists and it's not 0, which means that there's some kind of slope everywhere else. And so it must be going constantly decreasing down here, and then it flattens out here, and then increases up to that. So it looks something like that, and that means that must be the maximum, and this must be the minimum. Let's see what's next. Okay, so this is another kind of optimization sort of problem. If you are an archer shooting an arrow, and you want to know how should you shoot the arrow so that it goes as far as possible, this will be a helpful analysis. You'd have to do some physics first to get this equation. But it turns out, so if this is the distance from here to here is a distance of r, and you shoot it at this angle theta, if you ignore air resistance, then you can do some physics and find that just due to gravity itself, the distance it goes will be equal to the initial speed squared minus, times sine of 2 theta divided by g, which is the acceleration from gravity. And you'll have to trust me that all of these units work out. So if you want to know what theta maximizes r, we might need to think about first, what is the domain of this? Well, there isn't really one well defined, so we can't really use the extreme value theorem. But what we can do is start by finding critical points. So let's do that. I think you should try this one. Let's get the derivative of this and find out what values of theta make it 0 or undefined. It's a good exercise. So I'll pause it here, and part of the answers to this question, just for the critical points, will appear in 3, 2, 1. So here's the stuff we have so far, which is just taking the derivative of this, which is the v squared over g is all a constant multiple, so I left that alone, and then did the derivative of sine, which is cosine, and used the chain rule to leave the 2 theta plugged in and multiply it by the derivative of 2 theta, which is 2. And so if you set that to be 0, you know that none of these constants can ever be 0, because they're constantly something not 0. Oops, I mean never 0, not never theta. So that means cosine of 2 theta, this other thing must be 0, which we have over here. And so to see what theta should be, we need to see what is the input angle into cosine. Like what we're plugging, so to get this result to be 0, we need the x-coordinate to be 0. And that happens when the input into cosine is 90 degrees, or pi over 2. So that means that 2 theta would be pi over 2. That makes it so you're doing cosine of pi over 2. And then divide both sides by 2 to get theta is pi over 4. And then also, 2 theta could be 3 pi over 2 if you go around backwards this way. And then if you divide that by 2 to get theta, you find theta is 3 pi over 4. So these are both answers to this question. If you shoot it at an angle of pi over 4, it will go a distance to the right. If you shoot it at an angle of 3 pi over 4, it'll go a distance to the left. Or maybe if you turn around and do it the other way, then the angles will be different. So I guess it depends on which direction you want to go and which direction you're looking at the archer from. But either way, these are the ones that maximize it. But again, we have this issue with, we don't quite know what the domain is. I guess we could set it up to be something that makes sense in the context of archery. But let's actually look at a quick graph of this just to make sure that these things make sense. So to graph this, it's going to look like a sine curve, except because of the 2 theta, it's going to have a frequency twice as high, or a period that's half as long. So let's draw a quick graph of that. And the graph looks like this, and I'm actually glad I did graph it because I realized that 3 pi over 4 is a critical point, but it makes this negative. So that goes along with your intuition that it goes in the opposite direction. But technically, if we're maximizing r, we want it to be a positive number. This is actually the minimum r, even though you're going really the same distance in the other direction. We want to say that a maximum number is the positive one. So that's going to be theta equals pi over 4. So that kind of makes sense if you think about shooting an arrow into the air or throwing an object. 45 degrees sounds like a good guess at a way to make it go as far as possible. I think that's usually what you do, sort of intuitively, if you want to throw something far. kind of a more or less 45-degree angle sounds good. Here's another sort of physical example where we have two atoms in a molecule, and the whole background story behind this is very complicated because it depends on how the electrons are configured, and I don't even know what these forces are exactly. Is it the electrical forces from the positive and the protons and the electrons, or is it something else? I don't really know. But at least we can do one thing to help understand this physical situation, even if we don't really know all the ins and outs of the chemistry, which is pretty complicated, if you really want to understand it. So this is the function. There's some kind of constant b and a, so this really defines a family of functions depending on what the b and a are, which they're going to be different for different atoms and different molecules, I assume. And their distance apart is r. We don't have units, so it represents some kind of, I don't know, microns or angstroms or some very small amount of distance, and that has to be positive. And we want to know what distance minimizes the force. That's a thing that would help a physicist or a chemist figure out the shape of a molecule. So to do this, we're going to see what makes the derivative of this force function 0, to see where there's a critical point here. And notice that we can't actually use the extreme value theorem because the domain is r greater than 0. That's not a closed interval. So we're going to have to know what the graph looks like a little bit. So first let's find the derivative. To do that, I'm going to start by just rewriting these fractions as negative exponents. So we can say that f of r is br to the negative 3 minus ar to the negative 2. That way you can avoid using the quotient rule, because I think the quotient rule is my least favorite one of the differentiation rules. Even though it has a cool rhyme, it's so complicated and everything ends up being a mess. I like to do whatever other rule I can if I can avoid the quotient rule. So anyways, the derivative of this using the regular old power rule becomes negative 3 br to the power negative 4 minus 2 ar to the power negative 3. And generally, if you want to set this equal to 0 to see what makes this derivative 0, where there's a critical point, it's a good idea to factor this, to write this as a product of some things. So one way I see you can factor this is you can take out an r to the negative 3, and then what will be left over is negative 3 r to the negative 1 power minus 2 times a. And let's see, this r to the power negative 3 is never going to be 0. This is really 1 over r cubed, and if the numerator of that is 1, it's never going to be 0. But this thing maybe could be 0. So let's set this equal to 0, and that way we can find the critical points. And to deal with the fact that you have this r to the negative 1, I'm going to multiply both sides of this equation by r to cancel out with that. And then 0 times r on the right side is 0. This distributes in to give you negative 3b r to the negative 1 times r cancels out to just become 1 minus 2ar. In this other term, they both get multiplied by r. And then you can add that to both sides and divide everything by 2a, and you'll end up with negative 3b over 2a equals r. And still, this is a critical point. We know the tangent line is horizontal there. We don't quite know if it's a minimum or a maximum. So if you want to know if this is a local minimum or a local maximum, let's say you have to do this without a calculator, is a thing you might have to do. I think the best way to do this without a calculator is probably just to see what the graph looks like near r equals 0, and see if we can use, and also near infinity, because that will help us figure out what the shape of it has to be like. We could use a second derivative test, but that actually ends up being kind of a pain to plug in this thing with the b and the a into a derivative with high powers of r like that. So let's look at the limit as r approaches 0 of this is. And looking at this, the b and a are constant. So maybe we should actually combine that into one fraction here and look at it as the limit as r approaches 0 of b minus ar over r cubed. And looking at this, the denominator, it doesn't really matter if you combine it like that. The denominator is approaching 0. The numerator is approaching b. So it's going to get closer and closer to this number divided by r cubed. And b is assumed to be positive. So that's going to make this whole thing be approaching infinity. Positive infinity. With 0, b, a positive number, divided by something approaching 0. So we have that, and then let's look at what happens to this as r approaches infinity. Well, as r approaches infinity, you have b divided by a bigger and bigger number, and a also divided by a bigger and bigger number. They're each just going to get closer to 0. So that one will just be 0. And then you can use this to draw at least part of a graph of f of r. It's going to look something sort of like this, where if this is the r-axis, then as you approach infinity, this must be approaching 0 out here. So it's either doing that from below or from above. And in between, it has some point, and there's exactly one point where it's flat. So if you think about what this has to look like, if it's always staying above this axis here, then if it has a minimum, and then it's going to have to come back down again, which is going to make it have another maximum. So it actually can't be up here because it would have to have 2 critical points, and we know it only has 1 critical points. And so, yeah, you can think about it for a while. Like, there's no way for it to have just 1 critical point and then go from decreasing and continue decreasing. It has to turn around at least twice to go from decreasing to continue decreasing. So the actual only way this graph makes sense is if it does something like this. And that way it can only have just this 1 critical point down here, which happens at negative 3b over r. Now, it turns out that this is actually going to be a negative force, which we think of as an attractive force usually. So these positive values of f of r here usually mean a repulsive force, meaning they're pushing each other away, and down here that means they're attracting each other. That way you can have them define 2 different directions. And the place the equilibrium will actually form is where the force is 0 right here. So if they wiggle a little bit closer, then the repulsive force pushes them away and they get farther away. And if they wiggle a little bit further away, then the attractive force kicks in and they get pushed closer. And so they end up like wiggling sort of around that kind of area, usually is what atoms do, I think. So that's the answer to the question. This actually does minimize the force. So let's try some practice problems. The first one gives you a grapefruit that is thrown into the air, and the path it follows, it goes up and down according to this parabola function, and we want to know what is its maximum height. And practice problem number 2 is where this is actually a sort of model that comes up when you're trying to minimize certain kinds of manufacturing related costs, I think, where a and b are positive constants. We want to know what value of q makes this as small as possible, but we're only allowed to plug in positive numbers into this. So let's try these. By the way, with problems like this, I'm not sure if I've mentioned this. You don't have to in your notes write down the whole problem if you don't want to. Some people do like to use their notes as a reference for video notes, and they want to write down the whole problem because it helps. But if you feel like you want to just do the problem and write your answer down, that's really okay with these. It's okay with me as far as checking off your video notes. When I was a student, I never liked to write the whole problem in my homework. So. That's okay. So anyways, but you do need to do it, and the answers will appear in 3, 2, 1.
Here's the answer to the first one. I haven't quite finished the second one yet because there's a little bit more to talk about that I want to do recording the work for that, the rest of it. But anyways, for the first one here, the derivative is negative 32 plus 50, and that's equal to 0, so you can find the critical points where the tangent line is horizontal. And that happens when t is 25/16, or about 1.56 seconds. And if you plug that into a calculator, you'll get 44.0625, plugging it into the original thing. I should be calling that y, because it's not really called f, but either way. Anyways, you know that that's the only critical point, and because the graph of this is a parabola opening downward, the original graph of y is a parabola, it must have one maximum, and its only critical point must be a maximum. So that's how you know that. Then for problem number 2 here, this is the derivative, negative aq to the power negative 2 plus b. To solve that, I multiplied both sides by q squared to cancel out with q to the negative 2. That results in just negative a times 1 in that first term, and then b times q squared in the second term. And then if you solve that for q, you get q is plus or minus the square root of a over b. But if the domain is only q greater than 0, that means the negative one doesn't matter, so we only want the positive one. So anyways, how do we know if that is a maximum and not a minimum, and how do you know that there isn't some other maximum or minimum? Well, we have to think about the domain and what happens near the edges of this domain. So if the domain is q greater than 0, one edge of it is 0. Let's just say this is a number line here, and then there's other points in the domain here, and you can go all the way out here towards infinity. So I want to think about the limit as q approaches 0 and the limit as q approaches infinity, so we can see like what is the shape of the graph. Does it come up from above or down from below, or is there like an empty hole or something? So this limit of this thing, the a over q part is going to approach infinity, and the b times q will approach 0. So that's going to approach positive infinity. This part is going to approach 0. So the whole thing is going to approach like infinity plus 0, which we can just call infinity. So that tells you about part of the graph. Then we also want to know about the limit as q approaches infinity of c of q. And that's going to be the limit as q approaches infinity of a over q plus b q, and this time the a over q will approach 0 and the b times q will approach infinity, so the whole thing will approach 0 plus infinity. So it approaches infinity in those two ways. So that means the graph of this is going to look something like, just to get a bad rough sketch, just so we can see what these features are. If this is the q-axis, as q approaches infinity, the graph is going up in that way somehow, and as q approaches 0, the graph has an asymptote there, so it's going to look something kind of like that. And it only has one critical point. Now that means it could like turn around and go back up like this, but it can't like go down and up and down. We know this function is continuous, so it doesn't have any weird gaps or anything in it. It's differentiable everywhere. So the only way you could have a continuous differentiable function that has these two limits is one that just goes down in the middle and then goes back up. So that critical point must be there. You must have a graph shaped something like this based on these limits and the fact that it only has one critical point. So this must be the square root of A over B, and so that minimizes the C of Q. So that's the actual answer to that question. So that's what this section is about, is looking at functions like this, trying to analyze what their graphs look like based on limits helps analyze it. Or if you know that the graph has a domain that is a... so I just want to go over this concept again really quick here. If the domain is like just the interval from A to B, then it's definitely going to attain a global max and minimum. So all you have to do, this is like the easy situation, is when you have this kind of domain, just find the critical points and the endpoints and plug them all in. To find a global maximum and minimum when you don't have that kind of interval, like it's not a closed interval like that, then you have to find the critical points and sketch a graph. And in order to sketch a graph, you might need limits, or you need to know something about the shape of it to know, like, does it go, like, just knowing that you have a critical point doesn't necessarily tell you, like maybe this value is a critical point here. You don't know necessarily if the graph is shaped like that, or if it's shaped like this, or maybe it goes up and like this. So you kind of need to know more about the rest of the graph. So that's what this section is about. We'll do some more examples of things like this in class, and I hope you have a good day, and I'll see you on Thursday.